Why are you taking the Okeechobee Bridge is what I want to know.
I don't think we did 14.
All right, people, let's go over the warm-up. I think most of you are almost done.
Move our tables back there.
I should even get a new one of these things. All right, I think I helped everyone with 1 through 3. It started to be 4 where we are getting a little bit confused. So on 4, we were given that f at 0 was 6, right? Was it 6? Yeah, okay. And then we were also given that f1 at -1/2 is -4, and f2 at -1/2 is -6. So f1 is just like taking the first 2 terms, like where it was first degree Taylor, and setting that equal to -4 and plugging in -1/2 and solving. Okay, so -4 minus 6 is -10. And then multiply both sides by -2. You get f prime is equal to 20. So then we can replace this with a 20. Then you can extend that to your second degree polynomial. -6 is for equal to p2 at -1/2, and I have 6 plus 20 now, -1/2 f double prime at 0 over 2 factorial is just 2 times -1/2 squared. And solving it from there would get you to -16. But really, I don't think the algebra is the struggle on this one. It was like understanding how I got there. So do we have any questions on this first part? Because really it was getting f prime to be able to get f double prime. That was like the whole thing. So P1 is equal to the f at 0 plus f prime at 0 times x. And you were given P1 at -1/2 is -4. So that's where like the plugging in happened right here. My highlighter thing is lagging. Okay. Any questions on 4? I felt like 2 and 3 were really good questions, but once we got those, then I think you could see how they were the same but opposites. And number 5, second degree Taylor polynomial for e to the -x over 2. Start off always, remember the Taylor polynomial is going to be f at, this one's centered at 0. So we're going to have f at 0 plus f prime at 0 x plus f double prime at 0 x squared over 2. The over 2 is the thing that a lot of people are going to forget to do. So then we have to find the derivatives. And I'm a little scared with some of our derivative skills, I'm just saying. So some people doing some crazy stuff. This is going to be 1/4. So now we're centered at 0, so f at 0 is going to be 1. F prime at 0 Hello. Wow, fancy outfit.
Where
Um,
is that me in the back corner?
yeah, I think I really
Yes.
So really your polynomial should have been 1 minus 1/2 x plus 1/8 x squared. And we were trying to approximate e to the negative 1/4. And here's where I was like shooketh that you couldn't figure this out. We're not plugging in e to the 1/4 for x. 9.9 times out of 10 in a polynomial, in a Taylor polynomial, you are not going to do anything with the actual number you're trying. Like, e shouldn't be in here. The whole point of a Taylor polynomial is that you don't know what e to the negative 1/4 is. So why are you going to plug in e to the negative 1/4? You literally don't know what that number is. That was the reason you were using a Taylor polynomial. But we were using the function e to the negative x over 2. And now let's figure out what x should equal. We have the same bases as each other. And even if you can't tell here, you could multiply both sides by negative 2. What should x equal? 1/2. So now we're plugging in positive 1/2. And we're going to have 1/2. And positive 1/2. 1/8. 1/2 squared is 1/4. Beep boop beep boop boop. 25 over 32. That was my brain doing the calculating that time. We will have to do a lot of like fractions. So maybe I should show you how to add fractions. The common denominator is going to be 32. So I need a 32 and then over 32 from the first term. This is really a 4, so I'm going to have to multiply by 8. And I have a 1. And then, subtract and add. And then we get to 25 over 32. Okay, on 6. 6, I think, is where our algebra skills are struggling. We're trying to get the coefficient of the x cubed for the Taylor polynomial for the function f at x is 1 over square root of 1 minus x about x equals 0. I'm going to rewrite this as 1 minus x to the negative 1/2. If I'm trying to do the coefficient for the x cubed, how many derivatives do I need? 3. So I need the first derivative. It's going to be negative 1/2, 1 minus x to the negative 3/2, but I have to slap the baby. So this really becomes positive 1/2, 1 minus x to the negative 3/2. Then I get the second derivative. It'll be negative 3/4. We got to multiply. Slap baby. Positive 3/4. Okay, third derivative. Oh, yay, I'm almost done. Okay, we're going to have negative 15/8 times negative 1, slap baby, positive 15/8. And we're about x equals 0. So I'm plugging in, I'm getting f triple prime at 0 would be 15/8. 1 minus 0 to the, it doesn't matter, power, because that's just going to be 1, is going to be 15 over 8. So is it 15 over 8? No. Why not? Right, because we have to do the triple derivative over 3 factorial. So this is the triple derivative at 0, but we do over 3 factorial. And here's another thing that I noticed. This was specifically on number 3. So anyone who initially got number 3 wrong, here's a suggestion for what you can do instead of multiplying badly. If I have a fraction over a fraction, it is, really I can make the 3 have a denominator and flip it, but I just don't think that you guys are seeing that. So instead, what you could think about is you have 15 over 8 over 3 factorial. It is the same thing as 15 over 8 times 1 over 3 factorial. Like, this number being in the denominator can just like stay in the denominator. Like, keep this as the whole numerator, and then the 3 factorial is the denominator. That's like to try to avoid you accidentally multiplying by 3 factorial instead of dividing by 3 factorial. Also, I see some of us not knowing how to deal with fractions well without a calculator, and it makes me feel sad. Yes, this is 15 over 48, but when you make the denominator get bigger to then reduce, it kind of like presents you with opportunities to mess up. What is 15 actually like if I break it apart to smaller numbers? 3 times 5. So if I do that, instead of making the numbers get bigger to try to make them get smaller, just initially break them apart and see what you can cancel. The only things that are going to cancel is the 3's. And you get 5 over 16. I mean, you've made it this far by doing it the way you've been doing it, so you're probably okay, but I'm just trying to give you some suggestions about like how to not make little simple algebra mistakes. A lot of this unit is no calculator, so a lot of this will come down to you like struggling with fractions and adding fractions or not, you know, so hopefully we can start practicing those skills a little bit. I get out your notes. Hopefully to this period I won't get cut off like I did last period. Yes. No. Because I didn't record it. Yes.
There were ones from like last year on it too.
I know, all the ones that are there are what I recorded last year. I just forgot to record them last year.
I really liked it because I only like zoned out for a second or two. But on the recording I can go back.
Okay, the Lagrange error bound is gives people some nightmares because it's almost always part of the free response questions. And I am of the opinion that I don't think that it's as hard as everyone thinks it is, but I am also good at math. So I don't know, but I just don't think this is that bad if you can understand what a remainder actually is. So the function, the whole point is that of what we've been doing so far is saying we have some function that we don't know how to approximate. We're going to use a Taylor, this is like the Taylor polynomial, to approximate a value as close as we can get to that function. And then Lagrange came up with an error that was like, well, this is getting us really close, but he came up with adding this last little remainder to it to then get you even closer. So the remainder, this little formula is helpful. It's also helpful to realize that the remainder and the error are interchangeable terms. So if we say remainder or we say error, they're synonyms. Now, then it would follow that if I subtracted the polynomial to both sides, I would have the remainder is equal to the difference in the actual function minus the predicted value. It's giving residual, actual minus predicted. Oh my God, that's crazy. It's almost like that's what the residual is. So this is the actual minus our predicted, what we're trying to get. So the actual function minus the polynomial is our prediction. It's going to give you your error. What the error is, we're thinking margin of error. So a margin of error, they do the actual, like if you're making some kind of product, what you want the size of the actual product to be minus what you actually had. So predicted, or like what you have, I guess, what you can calculate without a calculator. this relationship should be within a reasonably small, the difference between what we actually want and what we have should be really small, because it should be a good prediction. So we want to make this number be little. Okay, so we want that error to be a small margin of error. If the margin of error is too big, then you send it back. I send it back. Oh, no Seinfeld fans. Okay. So then we get a Taylor series has the Lagrange error bound. Basically, the Lagrange error bound is this number that you can add on to the end of a Taylor series. What that number is equal to is essentially the next term over. So like you have the next derivative over the next thing of factorials times x minus c to the next power. So this remainder is essentially the next term. But the issue becomes is sometimes getting the derivatives get really messy, or maybe you don't know exactly like how to approximate it. There's this little z in here, and I think that that's what our hands are being raised for. So the z is a number that is between the x value that we want to predict for and where we're centered about. So c is somewhere reasonably close to what we're actually trying to find, like sine at 0.1, and so x would be 0.1, and then c is where it's centered at, so maybe at 0 or something. So that z value is something reasonably close. The problem that people have is they're like, what would reasonably close be? If you're trying to then go to the next part of the formula, you really want to maximize the numerator to make this error be as accurate as it can be, the largest value in that interval. So we're going to see where this comes into play on example 2. If you're saying like, let's look at example 2. If we're trying to center it and try to find the maximum, we're talking about the maximum between 1 and 0 for the function, which is e. So if our function is e, e to the x, and we're saying the maximum of our function, we're saying what's the maximum between, which one's bigger, e to the 0 or e to the 1? E to the 1, and why am I picking 0 and 1 and not something else? Right, so you're trying to approximate e to the 1, and you're like, great, but like the whole thing is I don't know what e to the 1 actually is. We can have a reasonably close value to e to the 1, where this is like step 1 to becoming an engineer. E to the 0, we know what that equals. What is it? 1. E to the 1, you probably do know what e to the 1 is about, but thinking like an engineer and making the number be as easy as possible, what integer value would e to the 1 be closest to? 3. So we're going to use the maximum as 3. Even though we kind of do know that e to the 1 is 2.7, 1828, that's not easy to deal with. The whole thing with Taylor polynomials is to make the numbers be easy to deal with, so we're going to choose 3. Just like how pi is 3 and e is 3 if you're an engineer, it's like the same vibe. So we're trying to be able to estimate things in our head. Okay, so anywho, back to the previous page. If your trig function is sine, even if you're trying to find sine near like pi over 4, what's the sine at pi over 4? Is square root 2 over 2 easy to deal with? No. So what would the maximum value for sine that would always be easy to deal with be? No. 1. Sine and cosine, they max out at 1. They min out at -1. And then whatever their coefficient might be, if it's like a derivative situation, then you take that into account. But so if you're dealing with a Taylor polynomial that you're trying to find the maximum of that has sine or cosine, you just make it be 1. So let's look at example 1. We are doing the 3rd degree Taylor polynomial or Maclaurin, so it's under at 0. Third degree Maclaurin polynomial, and it's given. We didn't have to do anything. Yippee. So they gave us that. Use the Taylor's approximate to determine the accuracy of your approximate. The accuracy of our approximate is really found by you find the remainder so you get the remainder and however many decimals until the first non-zero term tells us how accurate it is. Decimal point. Decimal point. So if you get like P3 is at 0.1 is 2.573792, whatever. Like you get some numbers. Then you get your remainder and it'll be like, it should be a decimal. And it'll tell you how many, like if you have like 5 decimal places before a number, and that's how accurate your approximate was. I think you're here. Okay, so we're saying sine at 0.1 is about equal to P3 at 0.1. And P3 is that polynomial. Okay, what's 0.1 as a fraction? 1/10. What's 0.1 cubed? 1/1000. And then what's 3 factorial? 6. So you have 1/1000 times 1/6. So we have 1/6000. What would you have to multiply 1/10 by to get a common denominator? 600, not 6,000 because it already has a 10. So we're multiplying by 600. 600 minus 1 is 599. So we're saying that sine at 0.1 is about 599/6,000. This is our prediction. This is what we're thinking or estimating it to be equal to. Then we want to figure out our remainder. The remainder is going to give us the accuracy level. Okay, we are trying to, I'm just going to do the formula real quick. Max F4, because I think if I plugged it right in, you'd be like, what the hell are you doing? All right, so what trig function were we estimating? Sine. So then what is our maximum going to be? 1. Okay, so now we have 10,000 times 1/24. Not 24,000. 200. The 1 is multiplying, and you got to keep that 0 in the same spot. Yes. Right, but like when it's sine and cosine, the fourth derivative is gonna like stay fluctuating between sine and cosine, and it's Maclaurin at 0. But you might get to where it's 0, but again, we're trying to say the numerator there is the maximum value of that function near 0.1 and 0, even like no matter what derivative level is. If it's sine or cosine, it's always gonna be 1. Just like, one, make your life easier, but also because that is the maximum of sine and cosine. Okay, so then let's figure out what the actual error would have been. We also could do an inequality here, but let's not get crazy. The actual error is going to be sine 0.1 minus P3 at 0.1. And that would be sine 0.1 minus 599 over 6,000. So our actual error, we want to make sure that our actual error is less than the remainder. Probably shouldn't have colons there. So the remainder was 599 over 6,000. And it is, and it should be, but I want you to get your Desmos out just to confirm. Like, this is where we would probably stop. We might also set up a compound inequality. But I just want to confirm, like, what these numbers are so that way, without a calculator, you can see the relationship. Zeppelin? Oh, my bad. Bad highlighter job. Oh, no. I highlighted this one blue. Okay, 3 at 0.1 was, what color did I not use? This number, yeah. Oh, all of you without iPads, so sad. All right, use Desmos, type this in. Your Desmos can calculate sine 0.01. So do that, yep. Right, so we're seeing how close our estimation is. So this is the actual value. And this is what we're predicting it to be. And we're saying this number, we're seeing how close our error is. No, you're using Desmos to see what numbers they actually equal. Because right now I feel like 599 over 6,000 doesn't mean a whole lot to you. And like 1 over 240,000 doesn't mean a whole lot to you. But if you type it in, you can get the decimals. Yeah. And you can say, a lot of times they'll be like, is your actual value less than 1 over 100,000? And you'd be like, yes, my error is smaller than 1 over 1. Like, is this accurate to more than 1 over 100,000? Yeah, it would be. Like, we are more accurate than that. So the actual value we get should have been 8.331 times 10 to the negative 8. That was the pink part. And then our remainder thing we got was 4.16 repeating times 10. Yeah. Which one's smaller? No. Look at the scientific notation, the exponents. Which one's smaller? Left or right? Left. Even though it has an 8, it is smaller because it's like has 7 zeros before it gets to the 8. The right one has 5 zeros before it gets to the 4. Now, this remainder is telling us, if we had a calculator, if it was like a calculator style question, this tells us that we have 5 decimal points of accuracy. Right, so like you would just have to trust that you know things. But this is with Taylor, this is just trying to show you like how actually useful, like you only had to do 2 terms of a Taylor polynomial for sine to get to 5 decimal points of accuracy before you got like the first non-zero number. Yep.
I have 2 questions. First, is it still smaller even though it's an absolute value?
Yeah.
Wouldn't that mean it's a positive number?
No, this means that this has 1, 2, 3, 4, 5, 6, 7. This one has 1, 2, 3, 5.
Oh, so even if you put it as an absolute value, like that wouldn't change anything.
Right. It's just like the to the -8 has more zeros in front of that number than the to the -6.
Okay, I for some reason was thinking that meant it was negative. I don't know.
No, like yeah, I think you were thinking that it became 10 to the 6. It's not it doesn't change like the exponent
I
sign.
don't know what I was thinking.
Okay.
But then also, for the one in the green box, it has less than or equal to.
Mhm.
But then on the right, it doesn't have that. Like, oh, wait, was that there the whole time? Oh, okay. Because I was gonna say, I was like, wait, what?
The equals to is kind of just like a safety net in case there was like a moment where they did equal, but generally it should be less than all
So
the time.
once you get like your exact numbers, you can just make it less than 7.
Yeah, because you can tell that it is less
Can I
than.
use the equal to, so I use it all the way down? So and then
Love that for you.
so I don't forget
Zeppelin?
on the other side.
So is like will there ever be a situation where the actual error is larger than?
Great question. Yes. So if you were like a more typical question that would not require your calculator would be like, is your approximate accurate to 1 over 100,000, right? So is it accurate to that many decimal places? And you'd be like, yeah, this is smaller than 1 over 100,000. But maybe you got a situation that was like 1 more zero after that 1,000, and you'd be like, no, this is bigger than 1 million. And so then it would be like, is your polynomial a good estimate then if you only were using 3 terms? And if yours is bigger than the number they're asking you to like get it to be smaller than accuracy wise, you'd say no, it's not like a good estimate for it. All right, so now we're going to do E, approximating E. And we're going to get what it's surrounded by. This is like kind of more what I think a question you could expect to see, because you don't need a calculator. I just wanted you to have like a moment of like looking at what these numbers were actually telling you. So if we're doing a 3rd degree polynomial for e to the x, soon I'm gonna be asking you to just memorize these. But what would we have to do if I have f of x is equal to e to the x? What would the derivative of f of e to the x be? Is all of them going to be e to the x?
Yes.
Yes. So then, no matter what level of derivative, if we're centered at 0, what would all of the coefficients, the numerator of the coefficients all be? 1. So they'd all be 1. And they would be positive, yes. So we have e to the x, and we're trying to get a 3rd degree polynomial. So it means until the exponent of x is 3. We're going to have squiggly lines. Okay, f at 0 is 1 plus f prime at 0 is also 1 over 1 factorial times x to the 1 plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed. We are trying to approximate for when x is 1. So we're plugging in 1. Okay, so you got 2 plus a half plus a sixth. Questions on how I got the 8 over 3? So we're thinking that e to the 1 is about 8 over 3, right? And 8 over 3 is like 2.67. And so then you got, I don't know what that means, but okay. You'll catch me up later, okay? Keep me fresh. So then the next thing we're going to do is try to figure out our remainder. We're trying to do the Taylor inequality. The Taylor inequality, I should probably mention what that means. So the Taylor inequality is what we'll do on step 3. The Taylor inequality is saying f at x minus p at x should be less than the remainder. So we need to find p at whatever value and the remainder at that value.
What is PM?
This case is going to be 3.
No, I mean like, oh, like P. Oh, okay, never mind.
So like in our situation, we're saying e to the 1 and then p3 at 1. And then we have to figure out what r3 at 1 is. What?
The remainder is just like the next term we left out.
Essentially, but it has that maximum situation to make your calculations easier.
Well, what about like all the other terms you left out? Do they just not like down because they're much smaller?
Think like look at what's happening. You're having 1 plus 1 plus a half. It's getting smaller. Plus a 6. They're getting smaller each term. But remember what we talked about. We are the remainder is actually trying to find the maximum that the function we were trying to estimate could be in this situation. The situation we're in is that we're looking near 0 and 1. What did we decide the maximum was going to be? 3. And again, we're like, we know that it's not really 3. But like, is that reasonably close to what it would be? Yeah, it's like reasonable. So we're putting in 3 for that numerator, not 1. 3 over 4 factorial is 24. Shh. Okay, 3 over 24 is 1/8. All right, so we're trying to set up a Taylor inequality. It really wants you to give a compound inequality. This is just like what we did with the alternating series error boundary. The part of it that's absolute value that I think a lot of you screwed up on your test, now that I've graded some of the free response questions, is that you thought whatever you got when you add this over here was just the same exact number when you put it on the left side. So right now we have a compound inequality. I drop off the absolute values for the Rn because I've made it be positive. Now the absolute values get dropped off when I say, okay, the difference between E and P, oh, I should probably plug in the number. Do I have enough space? What was the number again? Thank you. Okay. So now I can say E minus 8/3 should be less than 1/3, and E minus 8/3 should be bigger than negative 1. I said 1/3. E minus 8/3 should be less than 1/8, and it should be bigger than negative 1/8. This is like the compound inequality thing. So whenever you have absolute value inequalities, you have like the original way that the inequality looked. And then if I multiply both sides of that by -1, I would flip the inequality and I'd flip the sign of the number.
So would you have the words like between the two parties?
Right, because now the making it between the negative and positive 1/8 is getting rid of the absolute value. Noah?
You have that E is greater than or equal to, greater than or equal to -1/8, but that it's less than 1/8. Is that supposed to be like a less
Oh,
than?
I just forgot to write my equals to. So you have E is less than or equal to 1/8 plus 8/3, and is bigger than 8/3, and then 1/8 minus 1/8. Getting common. Did I put that back? No, that's right. Okay. I feel like that looks weird. I'm gonna rewrite it. I think that your brains might break if I do it that way. Okay. So E is reasonably close to being between those two numbers. Let's get common denominators. The common denominator is 24. So the 8 needs a 3 and the 3 needs a 8. So you have 64 minus 3, which is 61. And then you have 64 plus 3. So man, 6, 7. So this is our Taylor inequality for this one. And 6, 7 over 24 is like kind of reasonably close to E. And 61 over 24 is also reasonably close to being E. Oh my gosh. It's like the perfect moment with the hands too. The hands actually make sense right here. It's like 21 or 6, 7. I mean 61 or 6, 7. Like which one is in between? Okay, so now let's do, I think we got enough time. I want to do example 4. He does, and he does it all the time. I don't think he actually knows what he's doing, but yes, he's like, yeah, but he's just like 6, 7, and then like he tries to give me math problems that either equal 6 or 7, and then I'm like, or 67, like he'll be like, Mom, what's 70 minus 3? And I'm like, 67. He's like, 6, 7. I'm like, yes, so good. Wow. Oh, I don't know about 41. He also told me at basketball camp on Tuesday, someone was calling someone else a big back, and I didn't know what that meant, and then I found out what it meant. I thought it meant you had a big booty, and no, it does not. I got that. I gathered. That was Olivia and Nicole helped me know that I was wrong. Thank you. Okay, anyways, our last example. Focus. This should be kind of quick. A quick problem. It looks scary because there's a lot of words. And because you're like Lagrange error bound. Okay, so we are saying the function g has a derivative of all orders, Taylor polynomial third degree. So n is 3. For g about 1. So we're doing like x minus 1 in the Taylor polynomial. The maximum value for g on the interval between 1 and 1.7, which is, look further into the question. They want you to estimate g at 1.7. That's why they're giving you this interval. It's because they're saying somewhere near 1 and 1.7 is what we're trying to figure out. The maximum values for the nth derivative are given in the table. What is the maximum error guaranteed by the Lagrange error boundary used to approximate g at 0.7? So you're doing R3 at x should be less than the maximum of g at 3 plus 1. That level derivative over 4. Oh, hang on. 3 plus 1. I'm gonna spell it all out for you here. Factorial. He said, never mind to blessing someone? What's wrong with you? Oh, I thought you were just being mean. I was like, oh, never mind. It's you who made that noise? So I take it back. Okay, so what level of n are you actually looking for the maximum thing? 4. Because this is to the 4, we are given the maximum. It told you that these are the maximum values on the interval for whatever level derivative. So you're getting 3.7 over 4 factorial. And then we're doing R3 at 1.7. If this was a FRQ, you stop. Do not go further. So you're just like DN. If it was a multiple choice, it would not be these numbers. Right? So like multiple choice, no calculator would not be these numbers. Multiple choice calculator, then you can plug into your calculator, but then like, what the heck is the point? You know what I mean? So if you had a calculator, you would get 0.037. This is the maximum distance or difference between the actual value difference between so the difference between, we didn't actually have to calculate T3 at 1.7. We didn't even know what G was. Like we didn't know enough information to get the polynomial, but what point these things are equal to is like how close our estimate was to the actual value was within 0.037 of accuracy. Not that good, but like, yeah, we're only accurate to like 1 decimal point. Womp womp.
Does that say T
T sub.
something?
Mm-hmm.
What's T?
T is the third degree Taylor polynomial.
Oh, but we were just using R. Okay.
How much time do we have?
We have 3 minutes.
It's 150?
Oh, no, we have 10 minutes. I'm so sorry. I wasn't here for this. Sorry.
Which one do you want?
I'm thinking number 2.
I'm not sorry.
Wait, one question?
Can I get through? Do you not know how to tie your shoe?
No, I do. I just made it.
Because I was going to say, I've been teaching my 6-year-old how to tie his shoe. I'm a little worried.